we're going to look at some geometric properties of our conics. Chord of contact. Here's an interesting fact about chord of contact. If the point that you're drawing it from, so the external point, is on the directrix, then the chord of contact should go through the focus. So it's a focal chord. So let's prove it for the ellipse. Now, T's on the directrix, so we're saying our external point's on the directrix. So instead of it being x0, y0, I now know the x coordinate is going to be the same as the directrix, which is a divided by e. Now we know the chord of contact is x0, so now I'll make that x a on e on a squared plus y0 on b squared is equal to 1. So the a on e cancels with the a squared on the bottom, leaving just ae on the bottom. Now the focus is ae naught. So if I substitute ae naught into that, yes, I do get 1. So the chord does pass through the focus. So yes, the focus lies on the chord of contact. In other words, it is a focal chord. So there's a proof of that little one. Which then leads us to this beauty. That part of the tangent between the point of contact and the directrix subtends a right angle at the corresponding focus. What on earth? So again, let's do it for the ellipse. Let's draw it up so we see exactly what we're talking about. Okay, there's the tangent. You'll notice I'm using parametrics for this one. So it's saying that part of the tangent between the point of contact, P, and the directrix, T, subtends a right angle. Remember, subtend, get 2 points, join it up to a third point. So that third point in this case is the focus. So basically we want to prove angle PST is 90 degrees. Subtends a right angle at the focus. Okay. Well, we know the equation of tangents in parametric form. Bx cos theta on A plus y sin theta on B is equal to 1. I can work out the coordinates for t then. I know the x value is going to be a on e. Substituting that in and rearranging it, eventually I get y is b outside of e minus cos theta on e sin theta. Okay, so I have the coordinates for t, I have the coordinates for p, and of course the coordinates for s would be ae0. Multiply the two slopes together. Let's see what happens. So the slope of PS, that's the easy one. Let's do that first. B sin theta minus 0 on A cos theta minus AE. Well, not a lot can happen there. I'll factorise the bottom. A outside of cos theta minus E. Slope TS, a little bit more involved there. I've got fractions on fractions. But let's tidy that up. I'm going to create a whole fraction on the bottom and then invert and multiply. The E's will cancel. What else have we got? I've got B E minus cos theta, A 1 minus E squared sin theta. Now I want to multiply these two things together and get -1. But that's where I'm going to need to use another relationship. Anyone spot what I'm going to use? Remember, B squared is equal to A squared 1 minus E squared. So in other words, I could rewrite this A 1 minus E squared as A squared 1 minus E squared over A, but then that just becomes B squared over A, which cancels and I'll end up with A. And now you can see when I multiply these two things together, I'll get -1 very easily. So multiply them together, sin theta cancels, B cancels, A cancels, and you've got a cos theta minus E and E minus cos theta. Leave me with -1. So I guess the trick to that one is recognising to use that property of B squared is equal to A squared 1 minus E squared. Okay, so yes, it is 90 degrees. Right, the reflection property, just like we had a reflection property with a parabola, you remember? There's a really beautiful one with the ellipse. The tangent to an ellipse at a point P is equally inclined to the focal chords through P. We're saying they're equally inclined. Basically, the angle of incidence is equal to the angle of reflection, the reflection property. So TPS should be the same size as T dash PS. The beautiful thing about this reflection property is, and I'll find the video, Have I shown you the elliptical pool table video? All right, I'll show you that after we finish the theory.
So can you explain again one more time?
Right. So what we're saying is the tangent there, we're saying these focal chords are equally inclined. In other words, they make the same angle with the tangent. Which basically we're saying angle of incidence is equal to angle of reflection. Mind you, they do tell me that the angle of incidence and reflection is actually the angle with the normal, not with the tangent. But, I mean, if the angle with the normal is going to be the same, then logically the angle to the tangent must be the same as well, because they're perpendicular. So we want to prove SPT is the same as S dash PT dash. I'm going to construct a third parallel line going through P. Now, ratio of intercepts of parallel lines. You'll also notice I've drawn a horizontal line in as well. So PT over PT dash will be the same as PN over PN dash. Right? So it doesn't matter where I draw my transversals, they will cut in the same ratio. Just rearranging that. So I've got PT over PN is the same as PT dash over PN dash. Yeah. I also know definition of the conic. PS is equal to eccentricity times the distance to PN. So if I substitute that in for the PN and the PN dash, that looks a bit messy like that, but the E's will end up cancelling and I get PT over PS is equal to PT dash over PS dash. Now the thing is, remember we just proved the angle at the focus is a right angle. So we're talking about two right angle triangles now where I know these ratios are equal in both triangles. Okay. So therefore if you look at one triangle, the triangle that has PT and PS in it, PT over PS would be the secant ratio of angle SPT. And PT dash on PS dash would be the secant ratio of angle S dash PT dash in that right angle triangle. Now if they're both right angle triangles, we're talking about acute angles. So they're both going to be positive and all that sort of stuff. So if their secants of the angle is the same, then the size of the angle must be the same. So therefore angle SPT is the same size as angle S dash PT dash. This one here, we sort of touched on it in one of the exercises, this idea would have been helpful, but now we're going to prove it. The focal chords always add up to be a constant number. That constant number actually turns out to be 2a. Quickest way of proving this, again, is using the definition of an ellipse. And I'll just draw in, there we go. So, PS plus PS dash, I want to prove it's going to equal 2a. Well, PS will equal eccentricity times PM. But PS dash will be eccentricity times P to M dash. But you're now talking a horizontal line there. So I know that distance, I can work that out very easily, M to M dash. It's just the distance between the two directrices,
2A.
which will be 2A on E, which will cancel with the E, and you get 2A. And so the two focal lengths always add up to be 2A. There is a similar one with the hyperbola, but instead of them adding together to give 2A, it's the difference between them will give you 2A. And can be proven very similar way. Now, this idea of using the focal, the definition of the conic, I should say, if you have to find the length PS, it's a lot easier to find a horizontal distance. So if you can make use of the definition of a conic rather than trying to find PS, if you can find the distance from P, which is just going to be X, to the directrix, which is A over E, it could save some time in a lot of these problems. Now using that idea, I should be able to solve this sort of locus question. Mod Z plus 2 plus mod Z minus 2 is equal to 8. It is in that form. A distance plus a distance is equal to a constant number. So if I see that, it's an ellipse. Because that was the definition we just proved, the two focal distances. So the sum of the focal lengths is constant. And in fact, that constant is 2a. So I know for this particular ellipse, A is 4. AE would be the focus. Well, if modulus of z plus 2 is representing the distance to the focus, then negative 2 and positive 2 must be the two foci. It means my ellipse is centered at the origin, which makes life easy. But that also means that AE must equal 2. So if AE equals 2, I now know the eccentricity is a half. I know A, I know the eccentricity, I can now work out B, because B squared is A squared 1 minus E squared. And it turns out to be 12 for B squared. So there's my ellipse. X squared on 16 plus Y squared on 12 is equal to 1. So it's a nice little locus question there. All right, we'll have a couple of days to play with these. So 6E, 3D, 3F.